So today we will be looking into your fourth experiment, which is nothing but to realize binary to gray and gray to binary code. Okay. So now I want you to tell me, why do we need a coding system? Is coding system necessary?
For security reasons, sir.
Good,
Encryptions.
good for making things secure, right? So whatever information is passed, we do not want the other end to know, and we do a sort of coding, and we'll be learning about the gray code today. Okay. Fine. So the components needed will be IC7400. Okay, I think by now you all know what is 7400, 7486. What are patch cards? Patch cards, what are they?
Wires, sir.
Yes, the
Connect.
connecting wires. Okay. This will be like a bunch, okay, a bunch of wires which connects from one point to another point, right? Okay. Then the IC trainer kit. Fine. So this gray code is often used in digital systems, okay, because it has the advantage that only one bit in the numerical representation changes between successive numbers. So once now we have this key map, right? How does a key map work? I think you all know, right? How does a key map work? Yeah. Can someone tell me how does a key map work? How do we use key map?
You fill the boxes according to gray code.
Yes. So
The
which
arrangement
means
is
this
according
is
to
going to be my 0, 1, 2, 3, right? 4, 5, 6, 7. So this is going to be our key map, right? And here I'm going to have 0, and here I'm going to have 1, right? Then here the initial one, what is it? 0, 0, and then what is the next one?
01,
Good,
01,
good, and then
11,
yes, it's 1, 1, and then
10.
1, 0, right? So we have seen this key maps extensively in our uh, theory classes, right? So even this K-map also works with the same concept of just one bit changing. Okay, just one bit changing. So here you can see it is 0, 0, and the 0, 0 is common. So the only change that you see here is between 1 and 0, right? Between 0 and 1. This is the only change that you can see. So similarly, if you try to compare this one with the neighboring one, okay, 1, 1 is common, okay, 1, 1 is common, but then the only bit that changes is your 0 and 1, right? Your 0 and 1. So this is the only change. So similarly, your gray code also functions on the same fashion, okay, where just one of the bits changes, right? Okay. So gray codes are also called reflected codes. Now this is important. Why do we call them reflected codes? I will tell you once we look into the truth table. Okay, gray code is an example of unweighted code. Then what is unweighted code? It means there is no specific weights assigned to a bit position. Just like how we have 8421, okay, where our MSB is most significant bit is having 8, and then our LSB, the least significant bit, is having the value of 1. But here there is no such thing. Okay, it is just random. The gray code can be used to represent digital data in digital communication system, right? So communications is one such important thing where we will be looking into because we will be using um, coding system. So the advantage of gray code over binary is that the number in gray code changes by only one bit as it proceeds. So in binary, that format isn't there, right? See, because we have 0, 0, and then 0, 1, 1, 0, 1, 1. So when I say after 0, 1, okay, then I will have 1, 0. So is there a single bit change here between these two?
No, sir. 2 bit.
Yeah, both the bits are getting changed, right? 0, 1, 1, 0, both the bits are getting changed. So in binary system, this single bit variation isn't followed. Okay, but in gray code, you can find that the single bit changes observed. Okay, so I hope you have understood as to what I'm trying to convey, right? Okay, so now you can look at the truth table here. As usual, we take the binary numbers of 0, okay, to uh, all high ones, okay, and this gray code is in such fashion where it actually follows your K-map, okay. So when I say K-map, okay, so when I say K-map, it means that first, let me just, yeah, so the numbering is like this, okay. It goes in this fashion: 0, 1, okay, 3, 2, and then 6, right, then 7, 5, 4, okay. So you can just have a look at it, okay, just have a look at it. So initially it is 0, okay, then 1, then it is 3, right? So after 3, then it is 2, right? Are you able to follow what I'm trying to say? Yes?
Yes, sir.
Yeah?
Yes, sir.
Okay. So it is 2, then after 2, then what number is here? 6, right? So 0, 1, 1, 0 is what? 6, right? So similarly, it goes in that fashion, okay? So it goes in this fashion in your K-map. Okay, so that's the pattern followed by your gray code numbers, right? Okay, so accordingly, these are even called reflected codes. That's because you can see here that let me just annotate so that it becomes easy. So here you find 0, 0, 0, 1, 1, 1, 1, 0. Okay, so this section is like your what? K-map. Okay, so similarly here also you see this section. Yeah, so here you can see uh, just a moment. The other set of 4 values. Yeah, so these 4 values here also you can see that it is 0, 0. See these 0, 0 is actually here. Okay, then you can find 0, 1. Okay, 0, 1 is here. It's just like a mirror image. Then 1, 1. Okay, and then 1, 0. So it is like a mirror image, isn't it, students? Are you following what I'm trying to say?
Yes, sir.
Yeah. So the same thing, applies even for your other half. Okay. For this half also, with this first 4, the same thing happens. Okay. And the next 4 also, the same thing happens. Right. Okay. So if we have to get these equations, okay, we can put these values in the K-map. Okay. and we can get exclusive equations for our um, values here. Okay, so if we can see G3 is equal to B3, so this G3's value is equal to B3. So if you compare, wherever there is zeros, you have zeros. Wherever there is ones, there are ones, right? So both are same. And then for G2, okay, for G2, this is the value. B3 and B2 are XORed. Similarly, for G1, B2 and B1 is XORed. For G0, B1 and B0 is XORed, right? So either you can remember the way it is written, okay, or you will have to um, understand the logic that is being taught. Okay, fine. So the easiest way actually to remember this is, you know, with the K-map concept which I drew, right? So this this one will be the most easiest way to remember the gray code. Okay, if not, you can even verify with the reflected codes in this fashion, right? So any doubts? Can I proceed?
Yes, sir.
Okay, thank you. So once we have the equations, as you all know, it's simple to get the logical diagram, right? So G3 is directly given to B3, and then the others are using the XOR gates. Similarly, once we have this, you know, we can even represent it in the form of our universal gates. Now the reverse is what being done here. Okay, so you can write the gray codes here. Okay, as usual, the concept that I have taught you. Okay, 0 0 0 1 1 1 1 0. Okay, and here you will have all zeros. Okay, then 0 1. See here also you can see a pattern occurring. Okay, so from here to here, yeah, so this is like 0 0. Okay, and from here to here, it is like 0 1. Okay, and from here, what is it, students? What is it? 1 1, right? And this last one is like 1 0. Are you getting me, students? Is there any doubts here?
Yes, sir.
Huh?
No, sir. No, sir.
It's all clear, right? Okay, any doubts, feel free to ask anytime. Okay, so this fashion can be used here, and here also, you know, you can find that you can divide them to um, 8. Okay, 1 2 3 4 5 6 7 8. Yeah, 8. And whatever codes are here, okay, it is reflected. So if these codes are starting like this, okay, these codes will start from here. Okay, so it's a reflected way of representing your codes. That's why these gray codes are also called reflected codes. And these binary is as usual 0 1 2 3 4 5 6 7 8 9 10 11 12 13. Okay, so the whole values. Okay, uh, 14, and then the full values. Okay, from 000, from all zeros to all ones, right? So once we have these values as well, we can represent them in the K-map. So once these are put up in the K-map, okay, we will get these equations. Once we have these equations, we can directly represent the logical diagram and the universal diagram. Okay, so this is about your experiment. Okay, wherein you are trying to convert from one form to another form. Okay, so here also you can see your B3 and G3 are one and the same, right? Your B3 and G3 are one and the same, and your B2 is nothing but XOR of G3 and G2, G3 and G2. Okay, and then your B1. Okay, B1 is your XOR of G3, G2, and G1. G3, G2, and G1. Right. So similarly, you can just verify, cross verify. Sometimes what will happen, even if one of the values here goes wrong, then you wouldn't get proper equations like this. Okay, so it's always good to slightly remember and then try to represent them in the key map. Okay, and it becomes easier for you all to cross verify things. Okay, so this is about your experiment, and I will be also sharing you a few more materials. Okay, wherein you'll have to refer them, and if any doubts, we can have another meeting. Okay, so any doubts here, students, till this concept taught?
No, sir.
Okay,
No,
fine
sir.
then. Yes, thank you. Thank you all. Okay, and we will get back to classroom. And any doubts, we can have another meeting.